So this is the Lanchester balancer. This has been taken from a sensor's note. This is the uh, four-cylinder engine. So here there is a helical gear, and with that helical gear there are two balancing gears. So the helical gear meshes with one of the balancing gears, and in these balancing gears there are two unbalances, and the helical gear and the balancing gear, the gear ratio is such that these rotates twice the engine speed, because the secondary force has got twice frequency of the engine speed. So the net centrifugal force which are coming from the unbalances, it actually balances the secondary force, and the pitch and these two balancing gears, their pitch point is directly under the center of the crankshaft, so that it balances the secondary force. So the pitch point of the meshing gears is directly under the center line of the engine, such that the resultant inertia force of the rotating masses counterbalances the shaking force S. So this is the arrangement for one balancing mechanism which is used by some manufacturer. Yeah. So now let us start the graphical method, which is also used to check the state of balance. Yeah, this is the graphical method. So here you see, this is the crank diagram 1, 4, 2, 3. So actually what we are doing is, so if this is the center line of the engine, connecting rod, crankshaft, then this unbalanced force is mr omega square r cos theta for the primary one, and cos 2 theta by n for the secondary one. So we are replacing this inertia force by a centrifugal force, with the understanding that the horizontal component of the centrifugal force is equal to the inertia force. So we are putting a mass mr here, which is rotating at omega. So again the centrifugal force is mr omega square r, and the component along this center line is mr omega square r cos theta. So in place of this we are putting a mass here. That means the centrifugal force is along the crank. So here for 1 and 4 the centrifugal forces are 1, 4, and for 2 and 3 they are 2 and 3. So we are starting from this point and we are coming back at the same point. So the primary forces are balanced. Here we have taken the crank for the one to be perfectly vertical, but it can also be at some angle theta, but for the sake of convenience we show it vertical. Okay, now for the couple what we do, so we are taking the reference here. So for the couple, so we are showing, though we know that the couple is perpendicular to the plane of the inertia forces, we show it in the same direction as the inertia force. And if you take 1 as the reference, then for the 1 there will be no couple, for 2 there will be couple with which is multiplied by a, so this is m r omega square r a. For 3 it is m r omega square r twice a, so the size of this should be twice the size of this. So this is a, 2a, 3a, and for this it is again 3a distance, so again it is coming back to the same place. So the primary couples are also balanced. For the secondary couples, what we do, so for the secondary forces and couples, what we do, we draw a secondary crank diagram, which is an imaginary diagram, where what the angles what we are using here, we assume that the secondary cranks are twice that angle. Like 1, for the angle 1 is 0, if you take this as reference, then angle of crank 1 is 0, so 0 remains 0. Angle of crank 2 is 180, so it becomes 360. Angle of angle 3 is again 540, so it becomes 180. Angle of 4 is 0 or 360, so it becomes 720. And if you now draw the cranks with this angle, then all the cranks come at this position, 1 2 3 4. So this is the secondary crank diagram, and this is rotating with a speed twice omega because it is a secondary crank diagram. And what you can do is, since this is the force, m omega secondary force is m r omega square r cos twice theta by 1 n, you can write it like this, m r by 4 twice omega square r by n cos 2 theta. That means this is the mass, this is the speed, this is the effective crank radius. So at r by n you put a mass of mr by 4, and this is rotating at twice omega. Now for the forces, so all the forces just add up because they are in the same direction. So 4 such things are added up. 4 such things are added up. So this is here, there will be 1 n will come. So 4 such things will get added up. That means this is 4 mr omega square r cos twice theta by n for 1, mr this cos for 2, for 3, for 4. So it is 4 mr's the omega square r by n cos 2 theta, and this cos 2 phi. For this you will get 4. And so this is, and if you just draw the couple diagram, then what you have to do is you have to draw the same diagram, only for 1 it is multiplied by mr omega square r by n, it is multiplied by a, it is multiplied by a. Then the next one, the same thing, multiplied by 2a, and this is actually for crank number 2, this is for 3, for 4, because you are taking the left one as the reference plane, and for crank number 1 there is no moment. So 2 3 4, so twice a, thrice a, so 6a m r omega square r by n cos 2 theta is the secondary unbalanced couple. So in this way you can just draw the diagram and check the state of balance.